Common subexpression elimination is a compiler optimization technique. It searches for instances of identical expressions. When it finds them, it analyzes whether it's worthwhile replacing them with a temporary variable holding the computation. For instance, we have two equations with a common calculations b multiplied by c that occurs in both equations. This would be worthwhile to save b multiplied by c in a temporary variable, since cost of storing and retrieving temporary variable is less than the cost of calculating the multiplications of b and c twice. Okay, let's talk about the principle behind CSE now. The possibility to perform CSE is based on available expression analysis. It is an algorithm that determines for each point p in the program the set of expressions that don't need to be recomputed. Firstly, every path from the initial node to p evaluates b multiplied by c before reaching p. Secondly, there are no assignments to b or c after the evaluation, but before p. To sum up the principle, it all comes down to the cost and benefit analysis. After it's performed, data gets sent to the optimizer that will calculate the next steps. It is simple, really. It is either worth to store the redundant calculations to a temporary variable, or it's not. If creating the temporary variable costs more memory power than evaluating the equation multiple times, the program simply doesn't use it. Okay, I've created two examples for an easy demonstration. Let's imagine we have a house stored in three variables: its length, its width, and its height. Length of the house is 60 meters, width is 43 meters, and the height is equal to 22 meters. We are also aware that our neighborhood consists of 425 houses, including ours. I've designed a simple code timer function, with a little help of Stack Overflow of course, which times how long each function takes to execute. In this example, we are just using the volume of the house, which is equal to the length times width times height, and the neighboring area, which is equal to length times width of each individual house multiplied by the number of houses. The common calculation used in both equations is length times width, and therefore could be reduced. We can see time differences between each function. First function that ran on 20,000 cases and didn't use CSE took 3.3 milliseconds, which is 0.4 milliseconds longer than the same function that used the CSE. Therefore, we can see that the CSE indefinitely shortens the process. Second case ran on 20 million cases, and the function with no CSE used took approximately 3.25 seconds, while the second function on 20 million cases took 3.115 seconds, which is 0.113 seconds shorter. We can clearly see that the gap between times gets bigger when we increase the number of cases that we use, or when we run the code for longer periods of times. Okay, this second example is almost the same, but with more variables used. Originally I wanted to include it because using CSE wasn't faster, but then I found my mistake, and basically I forgot to implement the temporary variable into all the instances that it was used in. So here we want to calculate how many ping pong balls can fit in our house. I got a similar question in my product manager interview last week, where I was supposed to estimate how many ping pong balls can fit in Boeing 737. So yes, this might come handy someday. For this example, we will need the ping pong ball radius, which is 2 centimeters, and the ping pong ball's volume, which can be calculated by an equations 4/3 multiplied by pi multiplied by radius squared, which I did. Additionally, we have the weight of each ping pong ball and the weight capacity of the truck that will bring the ball, so we know how many trips must be made. Additionally, we have the weight of each ping pong ball and the weight capacity of the truck that will bring the balls, so we know how many trips must be made. Okay, so we calculate the volume of the house, a number of ping pong balls that can fit in the house, which is around 33 million. Next, we calculated the weight of all ping pongs to fill the house and how many truck rides we will need in order to fill the house. If we wanted to cover only the base layer with ping pong balls for all neighborhood, we can calculate the neighborhood area, which can be stored as in the temporary variable again. Actually, I've tried not storing other variables, but somehow the code was faster because I don't think I've used it that much. So I decided to use the neighborhood area again, which is kind of boring, I know. In the results, I got much more volatility than in the first example. Sometimes CSE was barely faster, whilst in the other cases it was faster by 20 to 60% than not using CSE. CSE has proved to be useful on a range of problems. I don't think we directly mentioned CSE throughout the classes, but thinking about it, in a graph with many nodes, it would be possible to hash the trees for each subexpressions into buckets in order to determine candidates for subexpression elimination. Since all expressions are in a single basic block, this idea can be used for detecting duplicate code, for instance in a graph coloring, where the graph would be big. This approach might help us to save a lot of memory. I hope this presentation made sense, and I'll finish it with this meme. I'll also give you like 4 seconds to laugh if you want.